Humanity is pushing its hardware into increasingly brutal environments. Whether launching satellites into deep space, pushing currents through high-voltage grids, or navigating the human bloodstream, our standard silicon technologies are hitting a physical wall. In these extremes, silicon melts, fries, or simply fails. To push past those physical limits, engineers are turning to a highly unexpected solution, a material we traditionally prize as a decorative gemstone. Engineers now synthesize diamond atom by atom inside specialized lab reactors, achieving a level of structural purity that bypasses the geological timescales required for natural formation. Through chemical vapor deposition, microwaves energize methane and hydrogen gas until they form a superheated plasma. The molecules break apart in this field, allowing free carbon atoms to drop down and deposit onto a seed layer, stacking sequentially into a perfect, uniform lattice. This precise atomic engineering strips away the aesthetics and turns diamond into an extreme material, designed specifically for the harsh environments where ordinary physics maxes out. Take low Earth orbit and deep space. Sending aerospace hardware up there means exposing delicate circuitry to a barrage of cosmic radiation that routinely corrupts or destroys standard silicon components. Diamond survives this bombardment because it has what physicists call an ultra-wide bandgap. Electrons in its lattice require a massive 5.47 electron volts of energy to jump the gap and conduct an electrical signal. Visible light from the sun is too weak to trigger this, making the material solar blind. But high-energy radiation, like X-rays, easily crosses that threshold. This is a lab-grown diamond semiconductor wafer. Researchers are actively using this hardware to create radiation-hardened detectors for small cubes at space missions, testing their endurance by blasting them with 100 mega-electron-volt protons in the lab. To be clear, we are far from building an entire satellite computer out of diamond. The manufacturing is still too complex for that. Right now, it is grown with high purity for very specific engineering uses, like sensor components. But its solar blind property is exactly what makes it work in orbit. A diamond sensor can accurately detect extreme cosmic radiation without the sun's visible light washing out the signal. Back on Earth, our electrical grids and electric vehicle charging networks face a different enemy: extreme heat generated by massive energy loss. Right now, materials like silicon carbide and gallium nitride are the heavyweights for handling power infrastructure, but diamond beats them both. It has the highest electrical breakdown field and unmatched thermal conductivity, meaning it can handle higher voltages and clear out heat faster than any standard material. In theory, a diamond transistor could switch electrical frequencies at over 100 gigahertz and continue functioning smoothly in temperatures exceeding 600 degrees Celsius. The roadblock preventing immediate adoption is chemistry. To make a semiconductor work, you have to dope it, forcing impurities into the crystal to control the flow of electricity. Diamond's lattice is so tightly packed that injecting these impurities to create reliable P-type and N-type devices remains a massive engineering challenge. Establishing reliable diamond doping methods would allow the material's thermal properties to drastically shrink the energy overhead of electric vehicle grids and data centers. Our final hostile environment is the human bloodstream. It acts as a highly corrosive, defensive barrier that aggressively breaks down foreign materials before they can ever reach a target cell. This is where we use detonation nanodiamonds, carbon particles measuring under 10 nanometers. Unlike many other nanomaterials, their specific carbon structure is highly biocompatible and practically non-toxic to living tissue. This chart shows cell survival rates, measured here as MTT percentage, when exposed to various carbon nanomaterials. Looking at the blue bars for raw nanodiamonds, cell viability stays near 100%, even at a high concentration of 100 micrograms per milliliter. Meanwhile, the single-walled carbon nanotubes and cadmium oxide cause immediate, toxic drop-offs in survival. Because of this safety profile, researchers can modify the surface of nanodiamonds with polymers and biomolecules to shield fragile therapeutic drugs, releasing them slowly over time. Their tiny size allows for efficient cellular uptake, but it is that high biocompatibility that lets nanodiamonds circulate safely, serving as a protective vehicle for targeted drug delivery. Atomic engineering has transformed diamond into a customizable toolkit, allowing us to tune its physical properties for specific industrial goals. Depending on how you manipulate its surface and structure, the exact same carbon lattice can conduct blistering heat, survive unfiltered cosmic radiation, or safely carry medicine through the human body. We aren't going to replace all the silicon in our laptops and phones with diamond. It is too difficult to manufacture at scale. Instead, it serves as silicon's specialized partner, the exact material we deploy when ordinary physics gives out. From sensors orbiting in the vacuum of space, down to the high-voltage transformers of a city power grid, and into the microscopic depths of a human cell. Atomic engineering has effectively shifted diamond from a status symbol into a specialized toolkit for solving our most difficult physical bottlenecks.
Share this with someone who loves fun facts.